Welcome back to the deep dive. Today, we're doing something a bit different. We're jumping into a kind of high-speed time warp right back to the years around 1895.
Yeah, it was an incredibly concentrated period. Just bang, 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 discovery after discovery.
Exactly. So our mission today is to kind of unpack that, synthesize the sources, and really get a feel for how our whole understanding of physics, of reality, just flipped upside down almost overnight.
It really did. Before this short window, chemists kind of knew atoms existed, conceptually at least, but what was inside them? Total black box. The basic ideas people had were about to get completely smashed by experiments.
It's fascinating to set the scene, too, the world they lived in. You've got peak Victorian England on one side.
Right, and then you have France still kind of reeling from the Franco-Prussian War decades earlier. And there's this interesting context where French scientists were actually arguing that, investing more in science was key to restoring national prestige.
Wow, linking funding directly to national glory.
Absolutely. And technologically, it feels almost like another planet compared to now. Gas lamps lighting the streets, not really widespread electricity yet.
And getting across the ocean.
Hey,
Steamships, sure, but they still had backup sails, decades after steam engine.
backup sales. It's incredible. And communication.
Yeah.
Very few telephones. If you were in Paris and needed something sent quickly, you used the pneumatic post.
Oh yeah, that system sounds like something out of steampunk.
Yeah,
Sending letters in tubes with compressed air.
exactly. High tech for the time. And cars. Well, they were just starting. Rutherford saw some a couple of years later, noted that they made a terrible rattling noise.
And slow, right?
Oh, yeah, maybe 20 kilometers an hour. The big complaint about street pollution wasn't exhaust fumes. It was the smell of horse manure. That was the backdrop for discovering the electron.
Okay, so gas lamps and manure. How on earth were they doing the kind of physics that could probe inside an atom? What did the labs even look like? What were the tools?
Well, they did have some pretty serious kit, especially high voltage stuff. But preparing and using it, it sounds almost, well, medieval in some ways. Dangerous, certainly. Think about the Bunsen battery, a key power source.
Right, and the instructions for it. I love this detail from the sources. Checking the acid strength.
Yeah, if you didn't have the proper measuring tool, a hydrometer, the advice was basically to put a drop on your tongue. If you couldn't stand it, the strength was about right.
You cannot be serious testing acid on your tongue.
That's what the old textbooks apparently said. And keeping it running was intense work. Amalgamating the zinc plates meant scrubbing them with mercury while they sat in acid. We're talking kilos of mercury.
Yikes. So a lab assistant's job was maybe not the safest career path.
Probably not. And all this fiddly, hazardous prep work fed into the main piece of high-voltage gear, the Ruhmkorff induction coil. That's what gave them the sparks they needed for things like gas discharge tubes.
These were big, impressive machines, right? Like symbols of scientific power.
Oh, definitely. Status symbols for labs. The one at the Royal Institution in London, for instance, had something like 450 kilometers of wire in its secondary coil. It could throw sparks 10 meters long.
Wow. Okay, so they have these powerful, if slightly terrifying, tools.
Yeah.
But the mindset.
Yeah.
You mentioned the black box of the atom. A lot of leading figures didn't even really believe in atoms, did they?
No. That's what's so wild. There was this real tension. You had people who used the idea of atoms, chemists mostly, but then you had influential figures like Wilhelm Ostwald pushing what they called the energetic doctrine.
Energetics. What was the core idea there?
Basically, that energy was the only fundamental reality. Everything else, heat, chemical reactions, even matter itself, could ultimately be explained just by energy interacting, atoms, an unnecessary hypothesis, sort of a philosophical crutch.
And this wasn't just some fringe theory.
Not at all. Even Max Planck, who's about to, invent quantum theory, later admitted he was distinctly hostile to atomic theory initially. It took his own work on blackbody radiation to really convince him atoms were real.
So the old guard, people like Lord Kelvin, who famously thought physics was pretty much wrapped up.
They were about to get the shock of their lives. The whole foundation was shaky. Even if they didn't know it, everything was poised for a collapse.
Okay, so if the establishment felt physics was basically done, what was the first crack? The first big sign that something new was happening?
That really comes in 1895. And it comes from Wilhelm Conrad Röntgen, a physicist generally seen as, good, solid, but maybe not a superstar. This was his 49th paper.
Right, the discovery of X-rays. It's a famous story, but the setup really highlights how accidental, how unexpected it was.
Totally. He's working in a dark room, running a high-voltage discharge through a gas tube using his Ruhmkorff coil, of course.
Huh.
And the key thing is, he'd covered the tube completely in heavy black cardboard. No visible light could get out.
Yeah.
But he notices this screen coated with barium platinocyanide just sitting nearby on the bench is glowing faintly, fluorescing. Something invisible had to be coming from the tube, passing right through the cardboard and hitting the screen.
And the impact was immediate, wasn't it? Because he didn't just announce it, he showed people.
Exactly. He didn't just write up a paper saying, I found a new kind of ray. He sent actual photographs, pictures of hands, where you could clearly see the bones inside, even the rings on the fingers. That visual proof was undeniable.
People must have gone absolutely wild.
Oh, worldwide sensation. Hysteria, almost. The medical potential, seeing broken bones, finding bullets, was obvious to everyone instantly.
Yet Röntgen himself, the discoverer, he seemed kind of puzzled by what he'd found. He didn't really claim to understand what these rays were.
He was very cautious, yeah. Focused entirely on the experimental facts, what he could observe and reproduce. He didn't want to jump to conclusions. He did speculate briefly they might be something like sound waves in the ether longitudinal vibrations, but he didn't push it. He stuck to the data, even if he couldn't fully explain it. He knew it was big, though.
So X-rays were the first major shock wave, but they were seen as rays, right?
Yeah.
Like light, maybe.
Yeah.
Getting to the structure of the atom needed. Well, it needed particles. Which brings us to the electron.
Right. And for that, we actually need to step back just a tiny bit to 1894 and the Zeeman effect. Peter Zeeman, a young Dutch physicist.
Okay, Zeeman effect. What was the key observation there?
He found that when you put a light source, like a sodium flame, inside a really strong magnetic field, the spectral lines, it emits those sharp lines of specific color they split. One line becomes multiple lines.
Sounds pretty abstract. How does splitting light connect to tiny particles inside atoms?
Well, the connection came from the theory side immediately. H.A. Lorentz figured it out. He suggested light must be produced by tiny charged things oscillating inside the atom. The magnetic field affects those oscillations, hence the split lines.
Okay, makes sense. But the killer evidence was in the numbers, right?
Exactly. Lorentz's theory allowed Zeeman to calculate the charge-to-mass ratio, the M ratio for these little vibrating things. And the number he got, it was revolutionary.
Let's pause on that M ratio because that's the crucial bit for understanding this leap, isn't it? Why was that specific value so important?
Because up till then, the only charged things they really knew about and could measure were ions in solutions, like in electrolysis. And those ions always had an M ratio related to the mass of a whole atom.
Okay.
But the M ratio Zeeman calculated from his split spectral lines was way, way bigger, about 1,000 times bigger than for a hydrogen ion, the lightest known atom.
1,000 times.
Yeah.
So for that ratio to be so huge, either the charge had to be enormous
Or the mass pen had to be incredibly tiny, much, much smaller than a whole hydrogen atom. That was the bombshell. It strongly suggested there were things inside atoms, things much lighter than atoms themselves.
a subatomic particle. And that's where J.J. Thomson comes in, at the Cavendish Lab in Cambridge.
Precisely. Thomson took that hint and ran with it. In 1897, he did his famous cathode ray experiments. He used tubes similar to Röntgen's, but crucially, he applied both electric and magnetic fields to the rays.
To deflect them, right, and measure how much they bent.
Yes. By measuring those deflections carefully, he could directly calculate the M ratio of whatever these cathode rays were made of.
And the value he got, let me guess.
It matched Zeeman's hint. His number, roughly 2.3 times 10 to the 17th ESU per gram, though units were different, then confirmed that these cathode rays were made of particles with this incredibly high charge-to-mass ratio.
The electron.
The electron. Concrete proof of a fundamental piece inside the atom. It really blew the doors off the old models and finally gave a glimpse into atomic structure. It's funny, though.
What's that?
His work was so fundamental, discovering a basic constituent of all matter, but at the time it was kind of overshadowed by all the public excitement and the immediate uses of X-rays.
Yeah, the flashy discovery versus the deep structural one. We're setting the record straight here.
Exactly. Okay, so we have X-rays, we have the electron. There's one more major piece in this rapid-fire puzzle, radioactivity.
Which spins directly out of the X-ray discovery, doesn't it? Started with a question from Poincaré.
Yeah. Henri Poincaré, the great mathematician and physicist. He wondered if there was a connection. Since X-rays seemed to come from the glowing spot where cathode rays hit the glass in the tube, maybe fluorescence that glows some materials produce after being exposed to light, Maybe that also produced X-rays.
Interesting idea. So Henri Becquerel decided to test it.
He did. He had some uranium salts, uranyl potassium sulfate, specifically which he knew fluoresced in sunlight. So the plan was expose the salt to sun, put it on a photographic plate wrapped in black paper, and see if any penetrating rays, like X-rays, came off and fogged the plate.
But then the weather didn't cooperate.
Classic experimental hiccup. It was cloudy in Paris for several days, so Becquerel just puts the wrapped plate and the uranium salt away together in a dark drawer, waiting for sunshine.
And then gets impatient. We're curious.
Something like that. On March 1st, 1896, he decides to develop the plate anyway, probably expecting maybe a very faint image at best.
But instead,
He gets this incredibly sharp, strong silhouette of the uranium crystals. Clear as day.
whoa. So no sunlight needed. No fluorescence needed.
Exactly. The
Yeah.
emission was just happening spontaneously,
Mm.
coming from the uranium itself constantly, regardless of light or anything else. He'd stumbled onto radioactivity, pure serendipity almost.
An amazing accidental discovery. And this new phenomenon, as they called it, that became the subject for Marie Curie's doctorate, right?
Yes, Marie Sklodowska-Curie. She decided to investigate these Becquerel rays for her thesis, and she needed a way to measure them accurately because they were pretty weak effects initially.
And her husband, Pierre Curie, had developed just the tool.
He had the quartz electrometer. It was based on piezoelectricity, the fact that quartz crystals generate a tiny electrical charge when you squeeze them.
How did that help measure radioactivity?
It was incredibly sensitive. She could use the tiny charge from the quartz to precisely cancel out and measure the equally tiny electrical current created as the radiation ionized the air. It gave her really good quantitative data, much better than just looking at fogged plates.
So using this sensitive tool, she starts testing everything she can find.
Right. And confirms Becquerel's finding about uranium, finds thorium is also radioactive, and then makes the crucial discovery. Certain minerals, especially pitchblende, were way more radioactive than could be explained by the amount of uranium or thorium in them.
Meaning there must be something else in there, something new and intensely radioactive.
Exactly. Which led her and Pierre on this incredibly arduous quest to isolate these unknown elements. First polonium, named for her native Poland.
And then the big one, radium. And the work involved sounds just brutal.
Oh, it was physically punishing. They got tons, literally a ton of pitchblende residue from a mine in Bohemia, and they had to process it chemically, by hand, mostly Marie, in this awful, drafty, leaky shed, boiling vats, separating fractions, back-breaking, dangerous work.
And all the while they're being exposed to intense radiation, though they didn't fully grasp the danger then.
No, not at all. It undoubtedly contributed to the health problems they both suffered later. It was immense personal sacrifice for the science.
And despite that sacrifice, and knowing they'd found something potentially valuable, they made a very specific ethical choice about it.
They did. They deliberately chose not to patent their method for isolating radium. Their view was that scientific knowledge should belong to everyone, be freely available.
Which sounds incredibly noble, though the sources mention maybe some differing views.
Well, yeah. Hindsight is 20/20, but some argue that patenting could have provided crucial funding for their research, maybe allowed them better facilities than that shed, or even given them more control over how this powerful new substance was used initially. But their stated principle was openness.
And Pierre Curie kind of doubled down on that science-first attitude later, didn't he, with the Legion of Honor?
Famously. When offered France's highest decoration, he reportedly said, "Please tell the minister that I do not feel the slightest need of being decorated, but that I am in the greatest need of a laboratory."
Perfect. Give me the tools, not the metal. That really sums up a certain spirit, doesn't it?
It really does. That pure focus on the discovery itself.
So looking back at these 3, maybe 4 years, 1895 to 1898 or so, it's just breathtaking. You go from gas lamps, pneumatic tubes, and physicists arguing about whether atoms are even real, to suddenly having X-rays, seeing through flesh, identifying a fundamental particle smaller than an atom, the electron, and discovering that some elements spontaneously pour out energy. The whole picture changed.
Completely redrawn. And it was this dynamic interplay, wasn't it? Sometimes theory-led, like Lorentz explaining Siemens' data. Sometimes pure experiment-led, like Röntgen or Becquerel, finding things that demanded entirely new theories.
And the tools, too.
Yeah.
You have Röntgen with his sophisticated Ruhmkorff coil,
Right.
but then the Curies making world-changing discoveries with a sensitive electrometer and basically a shack.
Right. And that contrast highlights something really important about this moment, this transition. It felt like maybe the last gasp of that era where where an individual or a pair could make these monumental, field-defining discoveries with relatively modest, almost home-built equipment, driven by sheer insight and perseverance.
Because what came next was bigger science.
Much bigger. To probe deeper needed more energy, more resources. It led fairly quickly towards the era of particle accelerators, huge collaborations, massive government funding. The scale, the cost, the whole way of doing physics was about to transform almost as much as the physics itself had just transformed.
From the shed to the synchrotron, in a way.
Pretty much. So the thought we want to leave you with as you ponder this incredible period is about that shift in scale. This brief, intense time saw these almost heroic individual breakthroughs with benchtop tools. Then came the move towards a massive, expensive, team-based science. How did that change in the process of science affect the spirit of discovery? Does needing a billion-dollar machine change the nature of the insights you find?
Something to definitely think about.
Yeah,
What gets gained and maybe what gets lost.
exactly. Food for thought.